So actually, I would say I'm here as a representative of the Lamar Institute, which I have the pleasure to have funded together with Stefan Rubel. And so that is my true home, in a way. Okay, so a tool that supports scientific research must be itself well based on scientific research. That's the main claim I want to make, because sometimes we might forget about this demand, and then we use a tool that is itself not well based, and then we cannot consider our results to be well based. Maybe it is trivial, but maybe it is not. So I just have written it here. So the overview of my talk will be that I talk about interdisciplinary research. And actually, machine learning has many relations with statistics. It has many relations with algorithms. It has very many relations with complexity theory. It is truly related to logic, as we have heard this morning already. It is truly related to computing and to cognition. So in a way, machine learning has very many relations to other disciplines, or they are part of the discipline, you never know. And then there is something which we might call the application area, or the particular area which machine learning wants to support. And then I call it the other area. It might be, in my talk, it will be, on the one hand, cognitive science, and on the other hand, it will be particle physics. So two very different other sciences, and examples are also medicine and so on. Protein folding, and so on. These are the other sciences. So there are very many motivations of AI research. And in the beginning, I thought I would talk about that for a while, and then I dropped it. Then there is logic-based learning, and I will actually start with logic-based learning to start with our first talk here in the workshop. So in a way, I come back to that, although maybe in a different setting, because it is multi-valued logic, and it is with knowledge revision. So it has some relations to what we have heard already, but I just use it for a case study in the theory acquisition of day-night cycle, interdisciplinary work that I did with a cognitive scientist for about 4 years. And then from that, I come to the overall scientific cycle, which is exactly relating to your talk. That's maybe then you understand why I was asking you that question. And I will refer to your talk in that part. First, by our first ice cube hypothesis, and then to our second ice cube result, which I would call evidence. and maybe these two directly show the cycle, the overall scientific cycle. And then I come to my epistemological claim of probabilistic rationalism, which is what I see. Well, there's a lot of theory in machine learning. I mean, it is, if you look at the large machine learning conferences, it is all about the theory of machine learning, which propositions are true for which model. And then the model is well defined, and it's just a little bit and so on. So, and what do we prove? We prove worst case runtime complexity. We prove probably approximately correct learning. We prove sample complexity. We prove object one Enquist dimension, Kolmogorov complexity, and so on. So these are all kinds of theoretical frameworks that, and then in my case, when I was a teaching professor, from PhD thesis to PhD thesis, we had a new proof of a feature of a certain type of a model. So that is what takes 4 years of intensive work, and then you get one of these proofs. Well, the complexity of decision tree learning, maybe that is the most well-known thing, that for n examples and m features, we have the effort of m times n log n. Why is that? Because we have the depth of the tree, that is n, and then we have the features, that's m, and then we have to spread all the features over all the depth, and that gives us the complexity of the decision tree learning. Then for feed-forward networks, we can say that it is very expressive. It can approximate any function to arbitrary accuracy using 3 layers of units. So that is a very powerful mechanism. Okay. Then today I will talk about inductive learning programming, because maybe it is more familiar to you, or it's more in the title of this workshop there was logic. So I thought, okay, let's go back to the old days and say there is concept learning, for instance, where we want to have we have given examples in the language of examples. We have background knowledge given in the language for background knowledge, and we want to find hypotheses in the language for hypotheses, such that EB and H are consistent. And the background knowledge and the hypothesis together imply the positive examples, and there is no negative example such that it is implied by the background knowledge and the hypothesis. So that is the consistency thing, and we have the completeness. Everything must be derivable that is to be derived, and nothing in the correctness is nothing can be derived, which is not. Okay, so that is a simple definition of the learning task in inductive logic programming. The good thing is the hypothesis can be many, many, many rules. Yeah, it is not just one hypothesis. Of course, theories are many, 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 many. So pro is that we have a direct representation of relations through the logical predicates. It is learning of logic programs that can be executed, which is not completely true, because in a program we have a cut. In a logic theory we don't. So, but if we take for a second this not into account, then actually we have logic and we can execute it at the same time. And then it is nice that we can include background knowledge, and it has a well-defined semantics, so we know the meaning. But there are problems, and that is that the semi-decidability of predicate logic holds for learning in logic. So the formalism must be restricted. And if we restrict it, we first do something about the inference. We say we take home logic and we take subsumption. As for the derivation, then it is correct but not complete. And yeah, and then in a way we can say deterministic clauses are learnable because each variable has unique substitution in the background knowledge. So deterministic means that the variables have a unique substitution. And then you see, aha, it is no longer very expressive. That is, yeah, that's what you get, right? It's a pity, but it is true. So now we can say, how far can we move the logic such that it is still tractable? So what is the space of logic formula such that it is still tractable? And then we have the IJ deterministic clauses, and there we have learnability proofs. So IJ deterministic is you have the def I and the number of arguments j. So for instance, you have the grand Ma, which is you have the mother of someone who is the mother of someone. The same is for the grandma, the father of someone and the mother of someone. So what you see is that ich kann ja irgendwie nicht mehr zeigen. Ich versuche das schon.
Eigentlich müsste das gehen. Ja,
jetzt kriege ich das hin. So what you have here is you have the chain, and you have the chain such that in the head you have a clear link to clauses in the body of the clause, and therefore it is deterministic. And indeterministic would be if you have the grandmother, a mother can have more than one child, and a child has two parents, and therefore it is not unique substitution. So the unique substitution makes it deterministic and binds the learnability and so on. So indeterministic is the list has more than one element, and it is not bound in the head of the class. Yeah, so if we take all the parents, then it is no longer deterministic. Okay, so this is now already quite a restricted logic, but it is one that we can polynomially learn. And therefore, whenever I do applications with a new science, for which I have no idea what it is about, for instance, protein folding or so, then what I always ask is, does your have exactly one? And if they say no, it can have several ones. I say, okay, then we have to change it. Okay, so by this you can easily see whether you can solve the problem with using machine learning or not. So we have a learnability theory for Horn logic, so that we know that even if the language of hypothesis is deterministic and function-free, and we have grounded and function-free examples and no background knowledge, even then, the consistency problem is empty space. And hence concept learning is empty space. There. So the maximum extensions of attribute logic that we can still learn efficiently, that is polynomially, are just this IJ deterministic clauses and KLL indeterministic Horn clauses, which I will not show you here. They are in my transparencies, but I don't want to bother you with too many formulas. It is just that we have found the one line which separates learnability from non-learnability. And it is depressing or not, it's exactly this. That's what it is. And yeah, and we have to have ground facts in the background and in the examples. If we there have also rules, it all explodes. So that is what we have as a true theory for inductive logic programming. And the proofs are old, they are from 1997. And from then on, we know that. And I will not. Nochmal?
Maybe click on the slides.
Oder was ist denn? Warum will der das nicht?
Einfach mal auf die Folie klicken.
Nochmal versuchen jetzt.
Einfach jetzt.
Jetzt kann man versuchen.
Och Mensch. Warum denn? Was ist denn das? Jetzt habe ich da. Ja.
Nochmal probieren.
Ja.
Das Ding ausgegangen?
So, jetzt. Die wollte ich ja gar nicht. So. Then, of course, we have lots of other learnability results. For instance, the famous Bloom-Rivest persistent set of weights for 3 neural networks with linear threshold function is NP-complete. So we have from Judd in 1990, training a 3-layer neural networks is NP-complete. Then we have the pack learning results. Each target concept can be learned from a polynomial number of training examples you have to show for pub learning. And then you have to show that processing time per example is polynomially bounded. So each such proof has these two parts, and their microcurrents has done many proofs from very many different types of logic languages, and the conjunction of Boolean literals are pack-learnable. So something can be learned. Horn clauses are not pack-learnable. That's why I had these things before. So in a way, why is this epistemologically important? It is so because what can we express in a given formalism shows which kind of knowledge can we formalize. Then what can we learn in a given formalism is important because it tells us what knowledge acquisition can we actually do by a machine. And then how do we know that what we expressed is true? That was also part of a talk before. We need some verification and falsification, because maybe it is just easily learned, and we show that it is polynomially learned, but it is false. I mean, this could also happen, so we must be careful what we do. Now I want to show you an interdisciplinary study with cognitive science that I did years ago with a full-fledged logic system that does knowledge acquisition, consistency checking, inference, and knowledge revision. So that's the logic system. And I did that together with Wozniacki and Brewer in 1992 and 1994 and so on. So it was a 3 years project, and we had empirical data from children from the age of 6 to 11 years old in first, third, and fifth grade. And they answered questions like, where is the sun at night? How does the sun show up again? How does it happen? Draw a picture such that it is day, and so on. So there were all these questions, and then the pupils answered these questions. And what I did was I made the valid model for the day-night cycle in logic, which is a nightmare if you have to write down all this, all these formulas with all the variable bindings and so on and so on. It took us really also about a year until we had that model cracked. So the correct physical model, because this is not an open question of physics. We know the day-night cycle. Okay, so we could model that in logic. So we have the true model, and then we have the models of the children. And then we change the models of the children only by inputting the minimum number of true facts, only true facts. And then knowledge revision changes the model as it is, such that it aims at covering the true fact. So we do this knowledge revision, and then we look at which model do we end up after that. And so we did that with all the models. And so, for instance, here is just an example of 3 models. So the one is between me and the sun comes something dark, and then it is night, and then this goes away, and then it is day again. Or it is the sun goes very far. So what you actually see is that the children use analogies to things that they know how they disappear. For instance, the one child said, yeah, I lost a toy in the sand box, and or I lost sight of my mother when she was running away. So these are analogies of the children. And so there's if. And then here is this model where the sun goes. Also be the case. So all this, and then it is expressed in logic, as you see here. This is the restricted horn logic that I talked about. And then we input true facts that lead to a contradiction. And our system has a minimal reversion, so it changes the minimal amount of knowledge such that the true facts are no longer in contradiction. And then I found it very interesting what happens. So we have the given models here, those that the children had as the starting point. And then we looked at all the revisions and where we ended up with these revisions. And then we found out that some lead in 2 steps, for instance, to the true model, and others cannot lead to the true model. So there we see the child just says something, bloop, 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 that it has heard, but it does not derive it from knowledge. And so we could see, there are possible ways of moving through this space, ending up with a true model. And the interesting thing is the complexity, because we saw that there are never more than 4 true facts needed in order to achieve the transition to the next model. And so we discussed that with the cognitive scientists, whether this is the true complexity threshold for children to learn, because and then they made additional experiments that if you add more than the 4 things, then they go back to the original model. They will not learn. It's too complex for them. So that is the collaboration with the cognitive scientists. And in that way, our model, in a way, allowed them to inspect further what children can learn and what they can't. Now let's come to astrophysics and see the overall scientific cycle. So we have some physical understanding, we have some data understanding, data preparation, modeling, and the evaluation. We come to some insight, and I call it insights. I do not know whether it is a hypothesis or it is an evidence, but we come to some insight. And this insight normally leads to a new question, which then starts all over again. So it is actually a cycle. And what I will tell you first as an example of this cycle is the death of the star. Well, we all know this famous Crab nebula that was observed in the year 1054 by Chinese astronomers, and then later in 1967 by Jocelyn Bell and her colleagues, it was found again. And so what happens is the heat of the dying star has turned electrons and protons to neutrons. And then you get a neutron star, and that is composed of neutrons. And then this neutron star may produce gamma rays and neutrinos. Then we finally are where we want to be. And there is this ice cube experiment from astrophysics. And these are 3 kilometer long holes in the ice of the South Pole. And here is the Eiffel Tower, and this is what they are. And there are optical elements in that. And in these optical elements, they they can see Cherenkov light, and Cherenkov light is nothing but a certain reaction of particles. So, and this blue light of the Cherenkov light can be measured, and then you can have measurements around this. And this is, for instance, right now, last week, 670 new sensors and equipment were added. So it is larger and larger, this area. And it will become even larger until the year of 2030. And yeah, and then what you get is you see these neutrinos trace through, and if they interact, there is a short blue light, and this short blue light must be captured, and then we analyze the data that come out of it, and it is 1 terabyte per day. So we have 1 million gigabytes, and the satellite takes about 10 years to transport the data. That's why the data are transported by a ship. Ships are much faster than the satellites in order to transport this huge amount of data. Okay, so then we have these data, and then we analyze them. And here you see what it actually looks. Okay, and then there was the first breakthrough, which was detecting the neutrinos actually in science, and we could see from where they are coming, what their energy is, and we found that the neutrino comes from this TXS blah 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 blah, 4 billion light years away from Earth, and we knew, aha, there it is. So you can sense from far away. And the nice thing was that gamma ray observatories, they measured the same thing. Okay, so in order to make it understandable, we did it with a rapid miner system. We did all the analysis, and it's very easy to understand. All the simple operators are well based in computational theory, and so on and so on. So that was the first IceCube result, and I was very happy because it takes 2 years until the collaboration agrees that this can be published. So I had to fight for cross-validation because they didn't believe in cross-validation. They said, if we do cross-validation, our results are much worse than yours. And I said, yes. Okay, so after all these years, all the collaboration agreed that this can be published. And then comes the next part. And the next part now is that in logic, and even using these nice standard machine learning operators that are theoretically well funded, you cannot express what is really going on. And therefore we had to come to, I didn't want to, I hesitated very long before I went to neural networks, but we had to, and the only thing I insisted on was, I want to have some estimate of uncertainty with it, so that we have some probabilistic component, and not just the CNNs. So we have the CNNs, and we did it on the data in a nice structured way. And then in the end, we also have a certainty estimate. How certain is the result? And so actually we could really find many neutrinos. So the issue is, and here we come to true multimodal things, there are not observable events which are only observable if you see neutrinos. So that black area could become bright because we had the neutrino. And then we see that all these pictures together and all these analyses together, they form the same picture of the Milky Way. And then I would call this no longer an hypothesis, but evidence. Because we have all this together, and there was this large press conference, and this is Mirko, who actually did the learning algorithm. He did it. I mean, a very, very bright PhD student of Wolfgang Rode and me. And therefore, we could then come and combine all the evidences, and from that, reach at something which I would call the breakthrough. Yeah, okay, but then I knew that everybody wanted to know about large language models, and we're talking about astrophysics. So there is a new project called Physics LLM, and another project that is called AA Learning. They both apply large language models to astrophysics, and this makes me come to the end of it. So we have seen the other science was here, the astrophysics, and what goes on in the Lamar Institute so these two projects are within the Lamar Institute. Tim Ruhr is the leader here, and this is the one by Lucy Fleck and others. Okay, so what does this have to do with science? Well, there's the world of observations, there's simulations generate what should be observed given the theory. Then there is the analysis, which finds what could be the theory given the observations, and then there are frequency distributions of courses and so on. So, and that's why Wolfgang and I came up with this probabilistic rationalism. What we think is the frame that we use for scientific analysis. So we say classes of physical theories are discussed simultaneously. They have very, very many parameters. They have diverse uncertainties. Hence, they cannot be handled as a further development of theoretical physics. They cannot be completely falsified. So all the logic with which I started is no longer possible. It is not possible to write up all this in that way. Instead, we have some parameter and uncertainty ranges that can be empirically tested. And we have some numerical values for the free parameters. And we do some random draw. So it is actually Monte Carlo methods and probabilistic. And therefore, we do not do it in the strict sense that I started with, but we become more modest and say, okay, let's do what we can. And maybe we find some truth, maybe serendipity will bring us to some insight, or maybe even to some evidence, but it is not a true space which we can search through. It is no longer possible, it is too complex. Yeah, okay, so we move from a binary logic to a multivalued, then from deterministic inference to probabilistic approaches, and finally to unforeseen adventures. That's it.